To finish up our discussion on techniques of integration, we're going to revisit partial fraction decomposition just really quickly. I want to point some things out. The course outline from the College Board concerning what is taught in BC Calculus says that as far as partial fraction decomposition is concerned, that we're guaranteed that we're only going to deal with linear factors. In other words, all the factors will only have powers that are linear powers. We won't see anything where we might have quadratic factors, right? Now, this technically is a quadratic factor right here. However, it can be written as two linear factors. Don't freak out if you see something like this. It is the product of two linear factors. So I'm not saying you'll never see quadratics. I'm just saying if you do, it can be written as two linear factors. This, however, cannot be. The sum of two positive things, we cannot factor that out. So we shouldn't see any quadratic or higher order factors. But that's not to say that we won't see repeated linear factors. And so that's something that I did not cover in the last set of videos. And so I want us to explore this. Because if we were asked to integrate something like this, it can be rewritten as the product of two linear factors. It just so happens those linear factors are the same factor. So if, as we would be highly tempted to do, we applied the process we did in our last set of videos, and we said, okay, a times the quantity x plus 2 plus b times the quantity x plus 2 has to equal 6x plus 7, we're going to have some issues. And our issues come right here. Because if I was going to add those two fractions together, those two fractions have the same denominator. The sum of those two fractions can be found like that. So you need to be really careful if you have repeated linear factors, because that's going to change what your original fractions, your a over b fractions, it's going to change them right up front. The only way that this is going to result in a common denominator of the quantity x plus 2 squared is for one of those to be squared. It doesn't matter which one. I could have squared the one with a in the numerator. But that's what's going to get me the common denominator of the quantity x plus 2 squared. Now beyond that, the process is the same. So we would apply what was missing, right, from our original denominator. The original denominator for this fraction has an x plus 2 in it. But what's missing is another x plus 2 factor. Do you see that whole well-chosen one show up there? So that's what that would look like. And now b doesn't have anything missing from its denominator, so it doesn't get multiplied by anything, and that has to equal 6x plus 7. I'll rewrite this term because we do have a times the quantity x plus 2 here. Well, it's going to be pretty easy for us to see a is going to have to equal 6 because it's the only x term over here. This would be a case where I think I would just go ahead and distribute, because you're not going to wind up with systems of equations here. Here, clearly, a has to equal 6. It's the only thing on the left side of the equal sign that is attached to x. However, 2a plus b is going to have to equal positive 7. When we know a is 6, then we have 12 plus b equals 7. b equals 7 minus 12. so negative 5. So we could evaluate that and find the antiderivative by taking 6 over x plus 2 minus 5 over the quantity x plus 2 squared. And all that is with respect to x. So this would have the antiderivative, 6 times the natural log of x plus 2, definitely. However, this antiderivative is not going to wind up having natural log in it. This is a u substitution where u is x plus 2, du is dx, but the integral winds up looking like 1 over u squared du, which does not have the natural log of u squared as an antiderivative. This is a power rule. Okay? The antiderivative here is, this would be negative 5 times negative u to the negative 1 plus c. So we need to be careful about that. So that would make this positive, and this would be 5 over, we could write it like that, 5 over the quantity x plus 2. So here would be the antiderivative when we had a repeated linear factor. So that's just different enough from the technique that we did in the last set of videos that I wanted you to see that. We could have more than 2 linear factors. We could have 3 unique linear factors. So I wanted you to see what that might look like. In this case, we would have 3 original fractions that were added together that resulted in what we have there in the numerator. Right? We're just applying the process. We just have an extra linear factor in the numerator than what we did before when we were working on things. So now we're still multiplying by well-chosen ones here. We still want a resultant fraction that has the common denominator when we get through multiplying things through. So, move that over a little bit. So what we're going to multiply by is we're going to have to multiply by both the quantity x minus 4 and the quantity x minus 2. And then we would repeat that process for b, and we would repeat that process for c. Now I'm just going to, again, mess with what's going to be in the numerator, because the denominators are all going to be the same, because I'm after a common denominator here. So b is going to be multiplied by the 2 factors that are not in its denominator, and c is going to be multiplied by the 2 factors that are not in its denominator, and all of that has to equal negative x squared minus 4x plus 42. So I don't multiply everything out. Don't do that. This is one of those times where picking values for x that force one of your terms to go to 0 is going to be really handy. Because if I pick x equal 4, that factor goes to 0, and everything multiplied by it goes to 0. And look here, it's in another one as well. So not only is that going to take care of a for me, it's going to take care of c as well. So what I'm going to wind up with is b times 4 plus 1 times 4 minus 2 equals negative 4 squared minus 4 times 4 plus 42. And that's how I find the value of b. And then whatever that value of b is, I'll put it up there and put it back in my integral. And so I would pick, let's pick x equal 2. That's going to force the a term to go to 0. It's also going to force the b term to go to 0. The only term that doesn't have the factor x minus 2 in it is the c term. So we have c times 2 plus 1 times 2 minus 4, and then we plug in 2 on the right-hand side everywhere that there is an x. and that's how we find the value of c. And now we would come over here and we would plug in x equal -1. That's going to take care of the b term and the c term, and that's how we're going to find the value of a. So a times -1 minus 4 is -5, and -1 minus 2 is -3. And again, everywhere there's an x on the right-hand side, we're plugging in -1. So I'm not going to go ahead and do all that algebra and waste your time, because frankly, I don't think you're going to see it on the BC exam. It's legal for it to be there. It's in the description. They could do this if they wanted to. But my argument once again is, look how much algebra you're doing to get very little return on their desire to test your calculus skills. So that's why we only really usually see two linear factors, two unique linear factors in the denominator. So since it's not as likely to be on the AP exam as what we did on the last set of videos, the homework that's attached to this lesson is going to be a mixed practice of all these previous techniques of integration that we've learned. Integration by parts, the new trig integrals that we looked at, and then the partial fraction decomp with just, two unique linear factors in there. So come to class next time and we'll do a mixed practice of techniques of integration.